The vast majority of the chemistry that we have looked at so far has all been to do with electrons. We're talking about ionic bonds, covalent bonds, it's all about electrons. Well, nuclear chemistry, as indicated by its name, is all about the chemistry of the nucleus, so we're talking about protons and neutrons. The first thing that we look at in regards to nuclear chemistry is isotopes. You should remember that isotopes are atoms of the same element which have different numbers of neutrons. And here is a nice dictionary definition for you to read if you wish. Here we have 3 isotopes of hydrogen. How do we know they're hydrogen? Because they each have 1 proton. Now it is the number of protons that an element has, that an atom has, that tells us what element it is from. In this case, all of these examples, these models, have 1 proton, so they're hydrogen atoms. Now normal hydrogen has no neutrons. It is just a proton and just an electron, and that is it. Now another isotope of hydrogen is deuterium. Deuterium has a neutron as well, so it is literally twice as heavy as a hydrogen atom, because a neutron and a proton weigh pretty much the same. And then we have tritium. Tritium has 2 neutrons. Once again, it is roughly 3 times the mass of a normal hydrogen atom. Other than that, they are chemically identical in terms of the way that they react with other elements. There is a specific way of writing down symbols for an isotope. Now obviously we've got the element symbol, X in this case, so for helium it would be Hg, etc. We've got the atomic number, that's the number of protons, and that's subscripted to the left of the element symbol, and we've got the mass number. And the mass number is the number of the protons and the number of neutrons together. So for a hydrogen atom, straight hydrogen atom, we would write it as H, 1, 1. The first 1 being the number of protons, which is 1, and the top 1 being the number of protons and neutrons, also being 1, because I don't have any neutrons in this case. For deuterium, we would write it as H1, and H is the symbol, 1 is the number of protons, and we'd have a 2 up the top, as that is the number of protons plus the number of neutrons, which is obviously just 2. And for tritium, we'd write tritium down as H, 1 and 3. One of the major things that we look at in regards to nuclear chemistry is this thing called nuclear stability. Now stability means durability, it means lasting nature, it means enduring nature, constancy, permanency, so we're talking about things that hang around. And if we're talking about nuclear chemistry, we're looking at things that are not stable. And we will examine some of the things that makes atoms not stable. We're going to introduce the word nucleons here. A nucleon is just a proton or a neutron, something that is found in the nucleus of an atom. If you look at this particular graph here, all these little black dots going up here, they all indicate stable atoms. Now on this graph we have got the number of protons down the bottom, and we've got the number of neutrons up the side here. As we get too big, as the atoms get just way too big above element number 82, which is lead, so anything above lead, you'll notice there are no black dots. That means that there are no stable elements, no stable isotopes of any element above lead. That means they all tend to fall apart, and that falling apart of an atom, of an isotope, we call radioactivity. There's one thing about atoms that you may or may not have thought about, and that is if we look at electrostatic repulsion. Now, electrostatic repulsion is the idea that if you have two like charges, like two positive charges or two negative charges, they will repel each other and opposite charges attract. Well, you think about a nucleus. So for example, if we've got a helium nucleus has got 2 protons, it's also got 2 neutrons, but in this case, if you think about 2 protons, they, from what we've learned so far, should repel each other, so the atom should just fly apart. What keeps atoms together, or nuclei together, or protons together in a nucleus, is something called a nuclear force or a strong force, and that is a force that acts at extremely short distances, which is an attractive force. Now that attractive force, that nuclear force, that strong force, overcomes electrostatic attraction within a nucleus and keeps the whole thing bound up together. Continuing on with our examination of the stability of elements, we are going to look at something called the neutron to proton ratio. Now, if we look at the number of protons up to about 20, so look somewhere along there, the number of neutrons to protons is 1 to 1. So here we're looking at Z equals 1 to 20, so that's up to calcium. We're talking about the neutron to proton ratio of about 1 to 1. So for every proton we have a neutron. The neutrons balance out the electrostatic repulsion of the protons and help bind the whole atom together. Now for Z equals 20 to 50, so that's from about scandium to tin, the number of neutrons needed to keep the nucleus stable goes up, so we're talking about 1.3 to 1. And for atoms bigger with more than 50 protons, we're looking at a ratio of about 1.5 to 1. So for every proton, we need about 1.5 neutrons to keep the nucleus stable. And once again, after we get to elements which have more than 82 protons, so anything bigger than lead, there are no stable nucleuses at all. They all tend to fall apart. The first type of radiation that we're going to look at is alpha radiation. Alpha radiation tends to occur with large atoms. Those are ones that are larger than lead, which are unstable. They have got too many nucleons, they've got too many protons, too many neutrons, and they tend to become a little bit more stable by getting rid of some of those protons and neutrons in the form of a helium nucleus. Now, this diagram over here, this one, it's the idea that here we go, we have a large atom. It becomes more stable by getting rid of 2 protons and 2 neutrons. Now, 2 protons and 2 neutrons just happens to be a helium nucleus. We would normally write the symbol for a helium nucleus as He24, and in this case, because it has no electrons, it has a 2+ charge. And over here, this little symbol there, that's the symbol for an alpha particle or a helium nucleus. Just some more details in regards to alpha particles. Well, this just shows that they've got 2 protons, 2 neutrons, no electrons. They're relatively heavy, and that's relative compared to other types of radiation, which we'll look at shortly. They are highly charged. Again, they've got 2 protons in the nucleus, but no electrons to balance out that charge, so they've got a +2 charge. We've got a strong interaction with matter, and that strong interaction is also due to the fact that they have a +2 charge. We've got a heavy damage to cells, so if they actually get into your cells, because they tend to strip electrons away, they can cause some damage. But that heavy damage is negated by the fact that they have got a very low penetrating power. So they can't actually get to the cells to actually cause any damage, because the alpha particles are blocked by skin, they're blocked by paper, they're blocked by clothes. So unless you actually ingest an alpha source, a source of alpha particles, they're not going to cause you any damage. Here we have a decay equation for the alpha decay of radium. Now, so we've got our radium here, it has 88 protons. It's decaying to give radon. Now, radon has 86 protons, and what's left over is a helium nucleus. So the helium nucleus is given off, so that goes shoots off, and we're left with radon, and so the radium has decayed into radon. In terms of looking at the numbers on either side, the atomic numbers on either side of the arrow, so on either side of the arrow, we've got 88, we've got 86 and 2, so the 86 and 2 add up to the 88. Also our top numbers, so we're talking about our mass numbers. We've got 226 for radium, 222 for radon, and 4 for helium. So the numbers over here Those two together add up to 226, balance with that. The second type of radiation that we're going to be looking at is beta radiation. The beta radiation has this particular symbol. Now, beta radiation is the emission of an electron from an unstable nucleus. Now, it seems a bit unintuitive because if you think of it in terms of electrons, the electrons are the things that orbit the nucleus. Now, in beta radiation, the electron actually comes from the nucleus. And how does it do that? It does that by a neutron turning into a proton and a beta particle, which is an electron. This particular diagram has got this particular symbol, which is called an antineutrino. We don't look at antineutrinos in our course. It's beyond the scope of this course, so you can just safely ignore that. Beta radiation tends to occur when we have too many neutrons in an unstable isotope. So, for example, our neutron to proton ratio, if it's outside of 1 to 1 for the first 20 elements, 1.3 to 1 for the next 30 odd, and 1.5 to 1 for the ones above 50, the atoms above atomic number of 50. If that ratio is wrong, if I've got too many neutrons, then some of those neutrons undergo decay by getting rid of an electron and leaving a proton behind. Now, beta radiation, because it's electrons, they are incredibly light. 1/1800th the mass of a proton. They have a relatively strong interaction with matter because they are negatively charged. Once again, moderate damage to cells, again because they're negative, they have a negative charge. They have a moderating penetrating power, especially compared to alpha particles. You think alpha particles, it's 2 protons and 2 neutrons, it's a fairly big particle. A beta particle is just an electron. It is absolutely tiny, and that means it's got a reasonable penetrating power. And in terms of penetrating power, electrons are blocked by, or beta particles are blocked by, a thin piece of metal. Here we have a decay equation for the beta decay of cobalt-60. Now, cobalt-60 is an industrial radioisotope which has many and varied uses. We'll look at that later. Now let's have a look at this cobalt. Cobalt has 27 protons. When it decays, it gives off an electron. Now the electron is written so that it has a -1 here. Now why do we do that? All of our numbers at the bottom, all of our atomic numbers have to add up. So if I'm starting off with 27, I'm getting a beta particle, which is -1, and I'm ending up with nickel, which is 28. And why does this happen? It happens again because I've got a neutron turning into a proton. So we have got, effectively, transmutation of an element. We're turning one element, cobalt, into another element, nickel, but we are removing a neutron, for want of a better term, and incorporating a proton. Neutron turns into a proton. So I've got one extra proton, so my atomic number goes up 1, so from 27 to 28. If you look at the mass number doesn't change, because the mass number is the total number of protons and neutrons. Now for cobalt-60 loses a neutron but gains a proton, so we've got no change in the mass number, but we do have a change in the atomic number. Again, we've just had a neutron turn into a proton and an electron is emitted, and that's our beta particle. If you look at the numbers, 27, we've got 28 -1, so that's 27, so that's balanced. We've got 60, and we've got 60 here, and that's 0. The third type of radiation that we're looking at is gamma radiation. Now the symbol is that. It's more often written sort of a bit more simply, just as swimming down fish is what I think of. Gamma radiation is an electromagnetic wave. So unlike alpha and beta, which are particles, gamma radiation is an electromagnetic wave. If you remember the electromagnetic spectrum, then we've got gamma rays are up the high frequency, short wavelength, high energy spectrum end of the electromagnetic spectrum. So they, generally speaking, have quite a lot of energy. So, electromagnetic wave, zero mass, zero charge, again because it's an electromagnetic wave. They have moderate damage to cells. They are highly penetrating. Again, because they're electromagnetic radiation, they go through quite a lot of material before being stopped. You need lead sheeting or heavy lumps of concrete to completely stop gamma radiation. And gamma radiation normally accompanies other decays. Now here's the same decay equation that we had for cobalt-60. Now when we're looking at it just as straight a beta emitter, so there's our electron, that equation doesn't actually show the fact that we have a gamma ray given off at the same time. Now once again, gamma radiation normally accompanies other decays. So in this case, cobalt-60, when it decays by beta emission, but it also gives off a gamma ray at the same time. Here we have an overview of penetrating ability. So we have our alpha particle, it's stopped by a piece of paper. We've got our beta particle, which is an electron, which is stopped by a thin sheet of aluminium or other metal. And we have got our gamma radiation, which is an electromagnetic wave, and it pretty much needs lead to stop it, fairly thick amounts, and even some of those get through, depends on how thick the lead is. One of the other characteristics that ionising radiation has, I don't think I've actually used that term, ionising radiation. Alpha and beta particles in particular are ionising because they can knock off electrons, strip electrons, knock off electrons from other particles. So they're called ionising because they turn other substances, other atoms into ions. But if I have got a charged particle and it moves into a magnetic field. So here we go, we've got a magnetic field. We've got two different magnets here, so we've got a magnetic field going from, say it's going from north to south, magnetic field. If I've got an alpha particle coming in, it is deflected by a magnetic field. And that's just a particular characteristic of if you have a charged particle moving into a magnetic field. To go with this, here we go, we have an alpha particle. Now these black dots here, they are showing a magnetic field coming out from the board towards you. They're shooting directly towards you. So I have an alpha particle. Alpha particles, if they are moving into a magnetic field, are deflected one way. Beta particles, or electrons, are deflected the opposite way because they have an opposite charge. You've got to remember that alpha particles have a 2+ charge, while betas are just a 1-. They are deflected in opposite directions. And we've got our gamma ray. Our gamma ray, because it is not charged at all, is undeflected and just goes straight through magnetic fields. It's now time to talk about something called half-life. Now, half-life is all to do with radioisotopes and how quickly they decay. So, for example, if I've got a radioisotope, let's just say it's called technetium-99m. Now, technetium-99m has a half-life of 6 hours. That means that if I have a certain amount of technetium-99, so let's just say 64 grams of technetium-99m. After one half-life, so in this case it'll be 6 hours, I've only got half left. I've only got 32 grams left. After another 6 hours, so that'll make it up to 12, then I've got only 16 grams left. After another 6 hours, so we're up to 18 hours, then I'm up to 8. After another half-life, so here we go, I'm up to 24, then I'm going to be down to 4. Another half-life, so I'm up to 30, I'm down to 2, etc. So it keeps on halving the amount of substance, the amount of technetium-99m as an example, halves after 6 hours. So half of it decays every 6 hours. Now half-lives can be vastly different. For example, uranium-235 has a half-life of something like 703 million years. When I've got technetium-99m, which has a half-life of 6 hours. We have other elements or other isotopes which have half-lives of microseconds. Here is a table just showing how many half-lives. After 0 half-lives, we've got 100% of whatever sample we have. After 1 half-life, we've got 50%. After 2 half-lives, 25%. 3 half-lives, 12.5%. 4 half-lives, 6.25%, etc. So it's halving every half-life. Hence the term half-life. As fractions, there's some fractions of the same thing. This graph shows the half-life of iodine-131. Now, you can straight off, I don't need to tell you what the half-life of iodine-131 is. This is just shows the mass. We're starting with 512 grams, 256 grams. Okay, so that's half of it gone. It occurs after 8 days. So the half-life of iodine-131 is 8 days. After a second half-life, I'm down to a quarter of what I had. After another half-life, I'm down to an eighth of what I had, etc. And it's an eighth of what we started off with. So there's the half-life of iodine-131. The decay of iodine-131 is a beta decay. So here's the decay equation. Now it's beta decay, how do I know? Because I've got an electron being given off. This also shows that we've got a gamma ray being given off, and I have got, in this case, let's have got our numbers. We've got an atomic number of 53, so that means 53 protons. We've got a beta particle or an electron. It's written as -1. -1 plus what gives you to 53, so that's 54. So I know that xenon is produced. So my iodine is decaying by beta decay, producing a xenon atom. Look at our mass numbers, 131, 131. Once again, one of the protons in iodine is one of the neutrons in iodine is turning into a proton, but my mass number does not change. My total number of protons plus neutrons does not change. And again, the electron has no protons or neutrons, so it has a 0 as a mass number. So the decay of iodine-53, of iodine-131, gives off beta and a gamma ray.